So we've talked about the human microbiota. Let's look at something different. Let's look at infectious disease. And this next section of the lecture is going to be more terminology and concepts for describing infectious disease. And then we'll get into more detailed studies of what causes it and how it is controlled. So first we get into things like opportunistic pathogens. This is a term you'll hear a lot because there are bacteria that will not always make a healthy person sick, but under some circumstances they will. And a lot of members of the normal microbiota are like this. One of the common species, often just classified as an anaerobe, is Bacteroides fragilis. It's a big part of the colon microbiota, but if it gets out of the colon, it causes it can cause deadly infections. So there's that. And skin bacteria, Staphylococcus epidermidis, if it gets into the bloodstream, it can cause endocarditis. And so anytime we lose that first line of defense, like anytime an epithelial layer gets breached, we get exposed to bacteria that shouldn't be there. So that's an important point, that, your skin microbiota belongs on your skin and your gut microbiota belongs in your gut, and they are not the same. And the microbiota from your teeth is not the same as the microbiota in your guts. They are specialized for what they do. Synergism is a general term when two things act together as more than the sum of their parts. And this is something we want to spend a little more time with than we did the first time. So if you think back to the very first lecture, we looked at Koch's postulates. And these were Koch's experiments that were able to really convince people that the germ theory of disease was the best theory. Because he was able, using these postulates, to convince people that Bacillus anthracis bacteria caused the disease anthrax. And so we used the same logic to prove, or to to prove that a certain microorganism causes an infectious disease. So here they are, and you should know them now. The first thing is we need to have observational data. Like, the same organism has to be present whenever the disease is present. This is really the first step. This is how you know what experiments to do, is you see this correlation. Then you have to get the pathogen into pure culture. So you have to take it from one of the diseased hosts, grow it in pure culture. And then you have to introduce it into a healthy host and induce the disease. So show that the disease will happen if you introduce this bacterium or this microorganism. So that is, the disease will not happen without it, the disease will happen with it. And then the last step is verifying that the organism you put into the host is the same one that you saw originally. So you isolate it again from the new host, and you compare it to the original. So that's the 4 steps, or the 4 postulates. And here's what it looks like in a more modern setting, where we start by we start by making the observations, but then we take the organisms from a diseased animal and we grow them in pure culture. And at the same time, we identify them, we characterize them, so that if we see them again in the future, we will know what we're seeing. Introduce them into a happy, healthy mouse, and then verify that the disease happens to that mouse. What they're not showing is that you should have other mice nearby, and you don't introduce the disease to them, or you don't introduce, the bacteria to them. And so they are healthy mice. They stay healthy. These ones get the disease. So then, from these ones, isolate the bacteria again, get them in pure culture, analyze them, and verify that they are the same as the ones you identified before. If you've done this, what you've done is shown that the disease will happen if you introduce that particular bacterium, but it won't happen if you don't. So another way of saying it is that this shows that bacterium or other microorganism is necessary and sufficient to cause the disease. When we do that, we can stop asking the question, what causes this disease, and start fighting against it. What slows us down is situations where Koch's postulates don't work, and we can look at each step and see what can happen. In the very first one, step 2, some organisms just won't grow. You can't grow everything in a laboratory. Not every organism will grow on solid agar, so it's hard to get them in pure culture. A bigger thing is we don't usually want to cause diseases in humans, so we want to use animal models when possible. And in some cases, there are no animal models. So one clear example of this is gonorrhea. It's hard to study gonorrhea because it will only grow in human cells. And so they are limited in their detailed understanding of what the cells do and how they work. There are other cases where different pathogens can do the same thing. So this would be like folliculitis, so infected hair follicles on the skin. Lots of different bacteria can do this because primarily it's a disease of the immune system or the immune system responding strongly to the presence of any bacteria. So Koch's postulates breaks down there, and that to some extent that's by definition, because you can't say that any particular bacteria is necessary to cause folliculitis because several different ones can cause it. Yeah, and then in other cases, there are complex diseases like tuberculosis that can lead to lots of different presentations, different syndromes. 2 people with advanced tuberculosis will not have the same signs and symptoms. The same for something like syphilis. There are a lot of complicated diseases like that. We need words like signs and symptoms. I will use these all the time. I already have used these a lot. Symptoms are the subjective things a person would notice, like malaise, like pain. Signs are what a clinician can measure. So a clinician can observe things in a patient and measure them, like temperature, blood pressure, response to stimuli, things like that. So signs and symptoms we typically put together, but you should know which is which. The syndrome is, well, there are 2 different uses of the word syndrome. A collection of signs and symptoms related to a disease is the disease's syndrome. Syndrome is also used for describing a disease that we don't understand at all. A syndrome can be a collection of signs and symptoms that we see together often. And so we say, oh, that person has that syndrome. But if we don't know what causes it, if we don't know why those signs and symptoms are there, why they're all there together at the same time, it's just a syndrome. And that's usually the first step, especially with things like viral infections, when it's hard to find the virus, because viruses won't grow on artificial media. You have to do detailed studies. First, you start with a syndrome, and then from there learn more about it until you can call it a disease. Infectious diseases can be communicable or non-communicable. Communicable means a person can pass it to another person. So a sexually transmitted infection or COVID-19 or cholera, whatever, those can be passed from person to person. Non-communicable would be like tetanus. You get it from environmental bacteria, tetanus, botulism, but you don't pass it to anyone else. And then contagious is a specific form of communicable. Contagious means very easily passed from a person to another. So Measles and chickenpox are the two best examples of this. A person with measles, fun fact, typically spreads it to 10 other people. So in the absence of public health interventions, a person with measles will give it to, on average, 10 other people. Compare that to COVID, where a typical person without public health interventions would give it to something like two other people. And a big question we have with COVID is, once we get people to lock down and wear masks, what does that number change to? How many people would an infected person give COVID to during a lockdown? And if that number is above 1, the infection spreads as an epidemic, and more people get it. If the number is below 1, then it doesn't, and it ends. So the idea with lockdown and masks is trying to get that number, that average number, below 1. These are different terms for disease severity. Make sure you read through these and can use these words. Let's see. We will talk about primary and secondary infections. Primary infection is the one that made a person sick. So the virus, for example, like SARS-CoV-2. So if a person gets this, they get COVID-19, that's the primary infection. They weren't sick before they got that. But then in the hospital, they get a secondary infection. And this can only happen after the primary infection. So something happens because of this virus to make a person susceptible to the secondary infection. And so it could come from the normal microbiota. It could, one example of this was influenza would make people susceptible to infections from the bacterium Haemophilus influenzae. And that still happens. And influenza makes people susceptible to streptococcal pneumonia. And that's what kills people who have influenza. And with SARS-CoV-2, they're seeing the same thing. And the sickest patients get really bad secondary bacterial infections. And so it looks like something happens, like viruses will disrupt an immune response and clear the path for certain bacteria to grow. And so Pseudomonas aeruginosa appears along with a lot of other potential bacteria in critical COVID patients. And once that happens, their prognosis is a lot worse. We can describe where different diseases come from. Most of the ones we think about come from outside of the body. They're exogenous. But endogenous diseases would come from the normal microbiota, and then some kind of change, some kind of problem that happens that allows them to cause a disease. This is some important terminology. Bacteremia is when we see bacteria in blood. Anytime you see bacteria in blood, that's bacteremia, and that could be serious or that could be trivial. So if you brush your teeth or floss, you get bacteria in your blood. The immune system wipes them out very quickly. So in a day, you would expect the bacteremia to go away. The much more severe condition is sepsis, and that's when bacteria or fungi grow in the bloodstream. So they're actively growing in the bloodstream. That is, they have overwhelmed the immune system, and the immune system cannot control the growth in the bloodstream. To declare that sepsis is happening requires a lot of other signs. Whoops, I forgot this. My predecessor put these in here, and much more The much more serious condition is sepsis. And sepsis is when bacteria are in the bloodstream growing there because they have overwhelmed the immune response. So the immune response is not controlling the growth of the microorganism. Sepsis can be caused by bacteria, fungi, anything that can grow in the bloodstream, but typically bacterial or sometimes fungal. Sepsis is accompanied by other signs. And so the medical condition of sepsis, which is a medical emergency, to declare it, to identify it, a clinician would need to see other signs. And when we get to this, this is something I'm going to expect you to know. Identifying sepsis early is a life-saving technique because it is a medical emergency, and the longer you wait to identify it, the longer you delay treatment, the more damage the bacteria can cause. So there are other signs to look for. There's a cluster of signs regarding blood pressure, temperature, respiration rate, things like that, that will typically happen if a person has sepsis. And so we will get to that later in the course. The next few slides are about nosocomial infections or healthcare associated infections. And yeah, these are a major problem. So a hospital is a very dangerous place for a patient to be. Any clinic that has people with infectious diseases becomes a way people can be exposed to them. So this is a big problem. Like a large fraction of hospital patients end up getting a new infection in the hospital. Tens of thousands of these end up being fatal infections. And so controlling this is a big challenge in healthcare, as we can imagine. So the most common would be the urinary tract. So UTIs are a big problem with nosocomial infections, but also, as we can imagine, surgical wounds and inhaling pathogens, all of them can happen. Let's see. And this slide lists a lot of common healthcare-associated pathogens, and you should learn these now. And when we study these individual strains in Unit 4, you will remember that. So Candida we've already seen. Candida can cause sepsis, and a lot of Candida strains are resistant to antifungal medications, and they live in hospitals. Staphylococci, either Staphylococcus aureus or others from the same genus but different species, they cause a large fraction of healthcare-associated infections, including the ones that are methicillin resistant that we talked about in Lecture 8. Enterococcus species, like the ones I used to study, I studied Enterococcus faecalis, which is a pathogen, causes most of these, and then Enterococcus faecium is often resistant to vancomycin. And so the vancomycin-resistant strains make up a large fraction of the Enterococcus healthcare-associated infections. And then E. coli, or Escherichia coli, I'm amazed that it still is a problem, but a lot of them would have antibiotic resistance plasmids. Yeah, so just know the ones in bold. And that's plenty for this video.